Hello, good evening. Welcome to the third week's session, problem solving session on introduction to the mechanical vibrations. So, in today's session, we will be going through some problems based on the content for this week, which was basically forced vibrations of single degree of freedom systems. So, in this course, the following topics have been covered, which have been listed over here. The first topic is harmonically excited vibrations. So it basically deals with the how to derive the equation of motion for for a system which is for which there is a sinusoidal force or harmonic force which provides energy to the system. Then the concepts about magnification factor and the frequency response curve have been discussed. So these are useful tools to assess the frequency response. Basically, so if we have a force that has a harmonic force for which the frequency, if we want to see the effect of the frequency on the response of the system. So for that, magnification factor is an important tool which basically talks about the extent of the steady state response with respect to the static deflection of the system. And the frequency response curve basically shows the variation of the steady state amplitude and phase with respect to the frequency. And then some particular examples of forced vibrations and resonance, which occur in many practical systems because of rotating unbalance. So, rotating unbalance means that there is some eccentric mass present in the system, and that eccentric mass causes a sinusoidally varying force, which basically caused some forced vibrations of the system. And in some cases, uh, it may lead to a resonance, which basically, so suppose if the speed of rotation matches the resonance frequency of the system, then there are chances of catastrophic damage occurring. So, for example, if there is a turbine blade which has some eccentric mass present in it, so then the rotating unbalance will, if it exceeds the if the frequency of vibrations caused because of the rotation speed. So if the speed of rotation it actually matches the resonance frequency, then there are chances of catastrophic damage to the turbine. Then the examples of excitation of the support have been discussed, where uh, the if there is some machine which is resting on some foundation, and there sometimes it happens that uh, there are like vehicles passing by or some kind of other vibrations which are causing the support to vibrate at a certain frequency. So then that may cause can some kind of undesirable vibrations in the system. So there are undesirable forces which may be transmitted to the system, so which we may want to avoid. And then the concept of energy input and the dissipation by use with viscous damping has been discussed. So with viscous damping, we are able to control the amplitude of the system. So these are the some of the topics that have been covered for this week. So let us now discuss about some examples of where we can see that resonance occurs. So let us go through an example video where we see resonance with tuning forks. So I'll be playing this video for you. So as we can see from this video, the person strikes a tuning fork which has a natural frequency of 512 Hz. He excites that tuning fork using some hammer, and then there is another tuning fork placed over here, which has two pendulums or basically balls attached through a string from this rod. So they have been suspended here and they have been kept in contact with this tuning fork. So now when we can see that when the person strikes uh, the tuning fork with the frequency of 440 Hertz, then we can see that the ball oscillates with significantly large amplitude, whereas when the person strikes the tuning fork with 512 Hertz, there are hardly any oscillations that are occurring, whereas with 440 Hertz, there is significant amplitude so that we can observe over here. So this is an example of forced vibration, and and we can see that the oscillations of large amplitude are basically being excited because of the frequency of excitation matching the natural frequency of this system. So that is called resonance. So let's go through another example of resonance with pendulums. So in this video, we could see that there are pendulums which are attached through a scale, and all of them are suspended attached to that scale, common scale, or horizontally, and they are suspended vertically through this common support. And each of the pendulum bobs have are suspended with strings of different lengths. So now what we can see is that the pendulum which has length similar or equal to the pendulum which was excited, that only that pendulum oscillates with significant amplitude. So now we can see that when the black pendulum was excited, only the pendulum which has length similar or nearly equal to that of the black pendulum, only that oscillates with significant amplitude. The rest of the other pendulums oscillate with very small amplitudes. Now, even in this example, we can see that even though the pendulum was given significant amount of amplitude of excitation, the other pendulums do not oscillate much. That is because their natural frequency is significantly different from that of the other pendulums. So these were some examples of post vibration and resonance. So we see many such practical examples of resonance being used. So resonance is a phenomenon which is important in musical instruments, and often it is used for tuning musical instruments. So let us go through some of the basic concepts related to forced vibrations. So we have this equation of motion for forced vibrations for uh, damped systems. So where damping is present, so C is the coefficient of damping, and M and K are the mass and stiffness respectively of the system. So we, on the right hand side, we have the force as a function of time. So this time varying force is usually we consider harmonic uh, oscillations, and so if there is no damping present in the system, and this force is varies in this way, f naught cos omega t, which is a sinusoidal force with amplitude f naught. So then we can derive the resultant steady state amplitude of the system, which is capital X, and we can describe that in terms of the static deflection delta St, which is basically the measure of the static deflection of the system. So then we can write the this relation as 1 upon 1 minus omega by omega n square. So where omega is the frequency of excitation and omega n is the natural frequency of the undamped system. So omega n is basically root of k by m. So now if we plot this variation of x upon delta static with respect to the frequency, then frequency ratio basically R is equal to omega by omega n. So then when the frequency ratio is 1, then we can see that the quantity x upon delta static becomes infinite because the denominator goes to 0, and for frequencies which are lower than for frequency ratio significantly lower than 1 and frequency ratio significantly greater than 1, we can see that the ratio of x by delta static is significantly small. So theoretically, the amplitude is infinite when the excitation frequency matches the natural frequency. Now if we do the same exercise for damped systems, so then we can derive the expression for the variation of the steady state amplitude of the system x with respect to the frequency ratio r and zeta, which is basically the damping ratio. So then we get an expression of this form, and the plot of this amplitude ratio with respect to frequency ratio is shown over here. So we can see that there are different sets of curves for different values of damping ratio. So as we can see that as we go on increasing the damping, the amplitude at the resonant frequency goes on decreasing, and for a certain for damping ratio values greater than some uh, limiting value, there is actually no resonance phenomenon that is observed. So for example, as we can see that when zeta is equal to 1, which is a critically damped system, so there is no peak for which represents the resonance, and this curve directly goes to asymptotically to 0 with increasing frequency ratio. So for very high damping values, the amplitude ratio falls rapidly and with respect to the frequency ratio, and we hardly see any resonance peak. Now if we look at the phase variation of the phase angle, then the as we go on increasing the damping value, the variation of the phase angle with respect to frequency ratio becomes more and more blunt, what you can say, and as we go on reducing the damping value, the variations become sharp, and near the resonant frequency, basically where frequency ratio is 1, in the vicinity of that, the variations of the uh, phase angle become more and more drastic. So so in the undamped case where zeta is equal to 0, there is sudden change in phase angle from 0 to 180 degrees. So this was about the content for the week 3. So now let us move on to some of the examples on uh, let us look at some example problems which are based on this content for this week. So let us look at the first problem. So in the first problem, it is given that when a damped system is excited by a harmonic force that has a magnification of 5 at resonance frequency, so then the damping ratio zeta will be what? So let us start with uh, the equation for magnification factor. So let us say magnification factor m. It is given by 1 upon square root 1 minus r square the whole square plus 2 zeta omega 2 zeta r whole square. So now, uh, so the definition of resonance is that the magnification factor will be maximum at resonance. So here basically R means omega by omega n, where omega n is the natural frequency and zeta is basically the damping ratio C upon Cc, where Cc is the critical damping. So then we want to find out the um relation of basically if we want to find out the frequency at which resonance occurs, then we have to differentiate the magnification factor del m by del r is equal to 0, or alternatively if we uh, so for basically for the based on the principle of maxima and minimum, we will have to equate del m by del r to be 0, or alternatively we could also say that the magnification factor becomes maximum when the denominator becomes minimum. So therefore we could also differentiate and equate del by del r square root of 1 minus r square whole square plus 4 zeta square r square is 0. So then we get basically 1 upon twice 2 root of whatever the denominator square the whole square plus 4 theta square r square. This into 2 into 1 minus r square into derivative of r square, which is minus r square, which is minus 2r plus 4 theta square into 2r is equal to 0. So which means basically the this expression would be 0 when the numerator is 0. So which means that so minus 4 r plus 4 r cube plus 8 zeta square r is equal to 0. So which means that r cube plus 2 zeta square minus 1 into r is equal to 0. So which means that either r is equal to 0 or r is equal to root of 1 minus 2 zeta square. So therefore, so let us find out. So this is the corresponding to the resonant frequency. So now let us find out the, so let us call this as R naught. So then let us find out the magnification factor at resonance. So that will be 1 upon root of 1 minus R naught square plus 2 zeta R naught whole square, which is equal to 1 minus 1 plus 2 zeta square the whole square plus 4 zeta square into 1 minus 2 zeta square. So this one will cancel and we will get so this will be magnification factor will be 1 upon square root so it will be basically square root of 4 zeta square minus 8 zeta to the power 4 plus 4 zeta to the power 4. So it is equal to root of 4 zeta square minus 4 zeta to the power 4. So if we neglect for small values of damping, we can neglect this term zeta to the power 4 and write it as it is nearly equal to 1 by 2 zeta. So then write it as it is nearly equal to 1 by 2 zeta. So so then therefore 1 by 2 zeta is equal to 5. So which will give zeta nearly equal to 0.1. So this is approximately the value of damping. We can also get an exact solution if we solve for the proper full coordinate quadratic equation which we will get in terms of zeta. However, if we want approximate solution, let us say if we assume small values of damping, and indeed we do get small value of damping of 0.1 only. So therefore, we can this is a reasonably good approximation of the actual damping ratio. Let us now look at another example problem. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So let us look at this example problem. Consider a spring mass system, a spring mass damper system with K is equal to 4000 Newton per meter. A mass is given as 10 kg and the damping coefficient is given as 40 Newton second per meter. So then we have to find the steady state and total response of the system under the harmonic force that is given, and the initial conditions are also given. So now we know that we can write down the equation of motion of the system as mx double dot plus cx dot plus kx is equal to f naught cos omega t, and then if if we want to write down the uh, break down the solution into two parts. So one would be basically the complementary function, which is basically the solution to the homogeneous differential equation where the right hand side is 0. So let us say if x is the solution, so we can write it down as xh plus xp. So then xh is basically the free vibration response of the system to the initial conditions, and xp is basically the particular solution or particular integral, uh, which is which represents the steady state response of the system to the forced vibration. So let us find out the particular solution. So for that, let us substitute a solution of the form xp e to the power j omega t into this differential equation. So then we would get minus omega square m plus k into x p e to the power j omega t plus j omega c into xp e to the power j omega t. And we could write the forcing also in a similar way, where f forcing we can write it down as f naught e to the power j omega t. So then xp e to the power j omega t into k minus m omega square plus j omega c is f naught e to the power j omega t. So then therefore we can write down the xp as f naught upon k minus m omega square plus j omega c. So in a complex number format. So this expression contains the steady state amplitude information as well as phase information. So we could say that the amplitude xp, which is given by f naught on square root plus omega square c square. So if we write omega n is omega n square, or rather omega n is square root of k by m, or omega n square is k by m alternatively. And zeta as the c by cc, where cc is basically 2m omega n, or 2 root km, which is basically the critical damping. Then we can simplify this expression as where r is omega by omega n, and the phase angle phi we can write it as omega c upon k minus m omega square. So this is how we can write down the particular equation, particular solution. So we can write down the particular solution as xp is equal to mod of xp, which has been derived above, into cos of omega t minus phi. And for the solution to the homogeneous differential equation, we can again write it down as sum as a function a cos omega n t plus b sin omega n t into e to the power minus zeta omega n t. So, so this should be actually damped natural frequency omega d, So this is uh, the solution to the homogeneous differential equation. So we can derive the unknown constants by substituting the initial conditions. So over here, the initial conditions are given that x naught is equal to 0.1 meter and the initial velocity is 0. So therefore, so xh at time t equal to 0 is basically a, which is equal to zero point 0.1, and xh xh dot is given by, if we can operate, we can find it by differentiating this expression for xh. So that will be minus zeta omega n e raised to by minus zeta omega n t into a cos omega dt plus b sin omega dt plus e to the power minus zeta omega n t into minus a omega d sin omega d t plus b omega d cos omega d into t. And if we substitute time t equal to 0 in this, we will get minus zeta omega n a plus b omega d is equal to 0. So this is, therefore p is equal to zeta omega n by omega t. So here omega d is basically omega n into root of 1 minus zeta square. So here we have assumed that the damping present in the system is, so that the system is under damped. So let us just check that. So here C is given as 40, whereas the critical damping value is 2 root km. So which is C is given to be 40. Mass is given as 10 kg and K is given to be 4000. So then the critical damping Cc is 2 root Km, and which is 2 into root of 40,000, which is 2 into 200, which is 400. So therefore zeta, which is basically the damping ratio, is C by Cc, which is 40 by 400, which is 0.1. So therefore the system is indeed underdamped. So our assumption of the homogeneous solution is correct. So now we can write down now the complete solution. So in terms of the initial conditions. So as we know now, A is already calculated as 0.1, and now we need to calculate P. So P is theta omega n by omega t, which is zeta omega n upon omega n into root of 1 minus zeta square, which is zeta upon A, and root of 1 minus zeta square. So this is the uh, value of B. We can substitute the value of zeta and find out the uh, value of this expression, zeta upon root of 1 minus zeta square into A, and thereby we can calculate the solution to the homogeneous differential equation. So we can write down the total solution as x is naught by k for the root of 1 minus r square the whole square plus 2 zeta r the whole square to cos of omega t minus phi plus a cos omega d t plus b sin omega dt into e to the power minus zeta omega nt. So we already have calculated the values of a and b. We have also written down the expression for phi, and we also have we know that this ratio r. So how do we know that? We basically have to calculate the natural frequency omega n, which is root k by m, which is root 4000 by 10, which is root of square root of 400, which is 20. So omega n is 20, whereas the omega is 10. So r is basically 10 by 20 or 1 by 2. So we can substitute the value of zeta and r, and we can calculate the value of phi as and using the values of zeta and r, we can calculate the phase difference phi from this. So this is how we can calculate the phase difference phi and the uh, the amplitude, uh, steady state amplitude. So now we have been given that our force F naught is F naught is 400 and our omega is 10 and our omega n is 20. So therefore R is basically omega by omega n, which is 0.5, and so we know x naught is 0.1 and the initial velocity is 0. So therefore A is x naught, which is 0.1, and B is basically zeta omega n A upon omega d, which is basically so zeta is 0.1. So B is zeta into A upon square root of 1 minus zeta square. So we now have calculated the value of B as well. So next we will calculate the uh, we have calculated the values of A and B, and now let us calculate the phase difference phi for the particular solution. So that is uh, tan inverse 2 zeta into r divided by 1 minus r square. So this is the phase difference phi, and now if we want to find out the magnification factor, so it will be basically 1 upon square root of 1 minus r square plus 2 into zeta into r whole square and square root of this. So magnification factor is 1.32. So the amplitude xp is basically f naught upon k, which is basically f4000 into the magnification factor m. So xp is 0.132 So the steady state amplitude value is 0.132. So these are some of the quantities that we can calculate using this method. So let us move on to the next example. So it is given that an industrial machine is weighing 445 kg and it is supported on a spring with static deflection of 0.5 centimeter. And it is given that the machine has a rotating imbalance of 25 kg centimeter and the rotating speed is 1200 rpm. So it has been asked that what is the uh, dynamic amplitude of the machine. So let us try to solve this problem. So let us first draw the figure for this problem. So it will be basically some machine. It is uh, weighing 445 kgs and it is supported on a spring with a static deflection of 0.5 centimeter. So from that we can find out the stiffness of the spring. So let us assume that there are some rollers which confine the motion of the machine in the vertical direction only, and let us say we represent the spring as shown in this figure. And so we know that capital M is 445 kg and K is something that we have to find out. So how do we find out K? It is by using the static deflection of the machine. So mg, the weight of the machine is supported by the static deflection. So K into static deflection delta St. So K, we can calculate it as 445 into G by delta static. So delta static is given as 0.5 centimeters. So we can say that G is 9.81. So it is 0.5 into 10 to the power minus 2 meters. So we can find out the value of K basically. So that would be 445 into 9.81 into 100 divided by 0.5. So it would be 873090 Newton per meter. So now we can find out the free body diagram for this. Uh, so because of the rotating imbalance, it is subjected to some force. So let us say F naught cos omega t, and it is also subjected to a spring force. Let us say Kx, where x is basically the displacement of the mass with respect to its equilibrium position. So we can write down F naught, because it is a rotating imbalance. We can write down as me into omega square. So it is already given that me into E is 25 kg centimeter, or 0.25 kg meter. So into omega square. So what is the excitation frequency over here? Omega. So omega will be 2 pi in by 60 into 1200. So in terms of radians per second, we will get, so it will be 48 to pi, which is about 125.66. radians per second. So this is the frequency of the excitation. And the natural frequency omega n will be root of k by m, so which is square root of, so the natural frequency will be square root of k by the mass 445, which is 44.3. So the value of r, which is the speed ratio, is omega by omega n, which will be approximately 2.837. So here since we have been given that we have not been given any damping value here, so we can say that zeta is 0. So the amplitude, or rather the amplitude ratio or magnification factor x by delta static, we can write it down as 1 minus 1 upon r square. And so which we can find out that, so therefore this magnification factor will be 1 minus, so 1 upon 1 minus 2.837 square, so it will be about 0.142 times the static deflection. So therefore the amplitude will be 0.142 times the static deflection, which will be it will be 0.071. centimeters. So that will be the steady state amplitude of this system. So hello, Nishu Kumar Singh. So I see that you have joined this session. So there were actually no participants till now. So thank you for joining this session. So so I have actually been taking this problem solving session for the last 3 weeks. So since there were no participants joined yet, I was just trying to solve some problems which I had taken from some of the previous year's assignments, and uh, based on that, I was, and also some other problems which I had picked up from various references. So I was just trying to demonstrate how to solve these kind of problems. So yeah, thank you for joining this session. So I wanted to know whether you have any particular question or from your end. So can you, before that, can you just tell briefly introduce yourself? So uh, no, can you tell like, can you just unmute and speak, please? So let me just tell you something about myself. So my name is Parth Joshi. So I am a PhD student at IIT Bombay and the recipient of the Prime Minister's Research Fellowship. And as a part of that, So I have been given an opportunity to conduct these tutorial sessions every week for this NPTEL online course. So if you cannot speak English, you can speak in Hindi or whatever language you think you are comfortable. I can understand Hindi, so if you can speak in Hindi, it's also fine. So are you able to understand what is going on? Because I am speaking in English. So till now I have like basically covered around 2-3 problems based on the content for this week 3, and I have been doing these online sessions for the last 3 weeks. And so have you watched any of the videos till now which I have made? So the recordings of the earlier sessions have been posted, and also the slides have been given to you. So have you watched any of the videos till now? आपने वीडियो देखे हैं? ओके. So you
यस सर,
have
देखिए
any?
सारा वीडियो देखिए।
हाँ जी, बोलिए. यस.
यस सर, सारा वीडियो देखे हुए हैं आपका। 2 गो वीडियो अपलोड किए हुए थे।
हाँ हाँ हाँ. तो आपको
देखे हैं सर।
आपको कैसे लगे वीडियोस? मतलब आपको कुछ काम के लगे?
यस सर, असाइनमेंट सॉल्व करने में प्रॉब्लम थोड़ा-सा मदद मिल गया सर, बहुत अच्छा लगा।
अच्छा अच्छा. तो आपको इस वीक के असाइनमेंट रिलेटेड या पहले वीक के कोई असाइनमेंट रिलेटेड आपके कोई सवाल है?
उम, बहुत सारा है सर, और वीक 2 में भी कुछ-कुछ प्रॉब्लम था सर।
हाँ जी, बोलिए. कुछ प्रॉब्लम हो तो बताइए. आई विल ट्राई. मैं ट्राई करता हूँ आपके क्वेरी को एड्रेस करने का.
यस सर।
कुछ बता सकते हैं? कोई पर्टिकुलर कोई प्रॉब्लम था ऐसे जिसको आपको सॉल्व करने में दिक्कत हुई थी?
यस सर, हुई थी। 1 मिनट।
हाँ हाँ, बोलिए.
नेटवर्क स्लो है।
आप स्क्रीन शेयर करना चाहते हो?
हुँ, टाइम लग रहा है यार।
आप स्क्रीन शेयर करके दिखाना चाहते हो?
शेयर ज़्यादा पता नहीं है सर गूगल ड्राइव के बारे में।
सॉरी.
सर असाइनमेंट 1 में प्रॉब्लम था।
असाइनमेंट 1
कोशिश
उस
कर सकते हैं शेयर करने के लिए। परमिशन।
एक मिनट, मैं जस्ट खोल रहा हूँ. आपको कौन से असाइनमेंट की बात कर रहे थे आप?
असाइनमेंट नंबर 1 सर।
हाँ हाँ.
क्वेश्चन नंबर 15 सर।
क्वेश्चन नंबर 15.
यस सर।
एक मिनट. हाँ, मैं आपको स्क्रीन पे दिखाता हूँ. तो क्या आप देख पा रहे हैं कि मैं क्या शेयर कर रहा हूँ वो आप देख पा रहे हैं?
यस सर, देख रहे हैं। यस सर, 15 नंबर क्वेश्चन ये।
आपको को 15 नंबर क्वेश्चन दिख रहा है?
यस सर।
The maximum displacement and acceleration of the foundation of a centrifugal पंप, ये जो था, ये इसी क्वेश्चन की बात कर रहे हैं आप?
यस सर।
ओके। तो इसमें दिया गया है कि द मैक्सिमम डिस्प्लेसमेंट is x is equal to 0.25 and maximum acceleration is 0.4 g. Find the operating speed of the pump. ओके। तो इसमें बेसिकली आपको क्या करना है कि मैक्सिमम एम्पलीट्यूड इज मतलब ये जो है जनरली सिंपल हार्मोनिक सिस्टम अगर एज्यूम करते हैं तो मैक्सिमम जो एम्पलीट्यूड है उसको उसका एम्पलीट्यूड लेटर से कुछ ए होगा, तो एक्सेलरेशन का एम्पलीट्यूड ए इंटू ओमेगा स्क्वेयर होता है, राइट?
यस सर।
तो इसका मतलब कि आपको ओमेगा स्क्वेयर कैसे मिलेगा? तो ओमेगा स्क्वेयर विल बी रेशियो ऑफ दिस एक्स मैक्स डिवाइडेड बाय एक्स डबल डॉट मैक्स, यानी तो आपको मेरी स्क्रीन दिख रही है?
यस सर।
हाँ। तो आपको दिया है कि एक्स मैक्स इज 0.25, राइट? और एक्स डबल डॉट मैक्स या फिर एक्सेलरेशन मैक्स वैल्यू दिया है कि 0.4 इंटू जी, तो जी मतलब 9.81। सो इसकी वैल्यू होगी 0.4 इंटू 9.81। तो बेसिकली ओमेगा स्क्वेयर विल बी इसका रेशियो, और ओमेगा विल बी इसका स्क्वेयर रूट। ठीक है, तो ये आ गया आपका ओमेगा, और ये होगा, तो इसको दिया है 0.25 मिलीमीटर में, और इसको दिया है 0.4 जी। तो हम अभी यूनिट्स की कुछ गड़बड़ नहीं करना चाहिए, तो इसीलिए इसको हम करेंगे 0.25 mm है, तो इसका मतलब हमें मीटर में कन्वर्ट करना है, तो हम डिवाइड करेंगे बाय 1000। तो क्या आएगी, एक्सेलरेशन की मैक्सिमम वैल्यू हमें दिया है और ओमेगा की वैल्यू दिया है। तो अभी ओमेगा की वैल्यू हमें पता चल गई, सो वो है रेडियन पर सेकेंड में। तो इसको कन्वर्ट करना है हमें आरपीएम में, राइट? राइट।
यस सर।
तो हमें आरपीएम में कन्वर्ट करना है, तो कैसे करेंगे? तो इसको मल्टीप्लाइड बाय 60 डिवाइडेड बाय 2 पाई, या फिर 30 बाय पाई से मल्टीप्लाई करेंगे, तो हमें मिलेगा 1196.371। तो आपका आंसर होगा 1196.97। तो क्या आपको समझ आया ये कैसे करना है? क्या आपको समझ में आया कैसे करना है?
सर व्हाइट बोर्ड पे सॉल्व कीजिए ना सर।
ओके, ठीक है। ओके, तो आपका व्हाइट बोर्ड में अभी ओपन हुआ है, आपको दिख रहा है राइट? तो नॉर्मली हम डिफरेंशियल इक्वेशन whatever for a simple harmonic motion we can write down differential equation as x double dot is minus omega n square x. So the general solution of this will be of the form a cos omega n t plus b sin omega n t. और acceleration x double dot is minus omega n square x, right? तो हमें क्या दिया गया है कि x की मैक्सिमम वैल्यू है 0.25। इसके पहले भी उन्होंने क्वेश्चन में क्या दिया है कि द मैक्सिमम डिस्प्लेसमेंट एंड एक्सेलरेशन ऑफ द फाउंडेशन ऑफ अ सेंट्रीफ्यूगल पंप। तो कोई सो देयर इज सम सेंट्रीफ्यूगल पंप और वो कोई फाउंडेशन पे माउंटेड है और वो ऑसिलेट हो रहा है अपने स्पीड के वजह से। स्पीड तो उसके रोटेटिंग स्पीड के अंदर के वजह से देयर इज सम ऑसिलेशन बिकॉज ऑफ दैट, क्योंकि कुछ रोटेटिंग इम्बैलेंस हो सकता है उसके अंदर। तो बेसिकली उसका जो frequency of vibration that is linked to its speed of rotation. So whatever natural frequency omega n resonant, so that is equal to the basically speed of rotation of the centrifugal pump. So x max जो amplitude whatever that is given, that is 0.25, and so that is in mm, and acceleration maximum value is so therefore omega n square into x max. So इसका मतलब है कि ओमेगा n square is acceleration's maximum value divided by x max, मतलब 0.4 into g divided by maximum value x of x is तो ये mm है, so that is therefore divided by 1000. तो इसलिए ओमेगा n is इसको स्क्वायर रूट जो भी आएगा, तो इसका आएगा वैल्यू 400 इंटू 9.81 डिवाइडेड बाय 0.25 स्क्वायर रूट। तो ओमेगा एन का वैल्यू आएगा 125 रेडियन पर सेकेंड। तो इसको आरपीएम में कन्वर्ट करना है तो इसको 30/π से मल्टीप्लाई करना पड़ेगा। तो 125 जो भी आएगा इंटू 30/π, तो उसकी वैल्यू आएगी अराउंड 1196। So you can solve it like this way, ऐसे ऐसे सॉल्व कर सकते हैं that। हाँ,
Yes,
यस, क्या बोल रहे हैं आप?
बोल रहे यस सर।
ओके, और कोई डाउट है आपको?
नो सर।
ओके, so then should we continue with whatever problems that I have planned? Should we continue with that, or you have any other question? आपको कोई और क्वेश्चन है?
नो सर।
ओके, ओके, okay. So then we will start with the next problem that I had uh, listed down. So here in this problem, we have been given that an automobile or car is modeled as a single degree of freedom system, which is vibrating in the vertical direction. So it is given that it is driven along a road whose elevation varies sinusoidally. So that means that कि रास्ते में कहीं पे बम्प है, फिर कहीं पे गड्ढा है, ऐसे करके अल्टरनेटली रोड बम्पी है। तो इसका मतलब ऐसे रोड का प्रोफाइल इट विल look something like this. The distance from the peak to trough. So distance between the extreme positions is 0.2, and the distance along the road between the peaks is 35 meters. So this is 35 meters. And it is given that the natural frequency of the automobile omega n is 2 hertz, and the damping ratio of the shock absorbers is 0.15. So we have to find out, so that when the car will go on this bumpy road, what will happen is that, so the wheels will be subjected to some forces because of, so basically the wheels are connected to the vehicle body through some suspension, which is a spring, basically a spring and damper. So so we can model it like, let us say the car mass is, we can model the car as a mass capital M, and the suspension has some stiffness and damping, and this is connected to the wheels basically. So we can draw the wheels like this, and so this capital M is the total mass of the car, and the small circle over here, that is basically the wheel. So it is going over this sinusoidal path. So let us say that displacement of the mass capital M with respect to its equilibrium position is given by x of t, whereas the motion of the center of mass of the wheels is given by some value y of t, which is again with respect to its own equilibrium position. So what is happening is that the motion of, or basically the displacement of the wheel is causing some spring force and damping force to be transferred to the car body, and that is causing some forced vibrations. And we have to find out the amplitude of vibration of the automobile at a speed of 60 kilometers per hour. So for that, let us write down the equation of motion. So before that, we have to find out what is the frequency of excitation omega. So let us call this distance between the two peaks as capital L. So the time taken to travel from one peak to the other peak will be basically the time period. So time is basically distance upon speed. So it will be L by V, where V is the speed of the car. So this will be basically the time period of the excitation force, and omega will be 2 pi upon T. So therefore omega is 2 pi V 2 pi V by L. So this is the frequency of excitation, and we have been given the natural frequency. So we have been given that V is 60 kilometers per hour. So which is in terms of meters per second, it is 60 into 5 by 18, which is about 16.67. So omega, which is 2 pi V upon L, will be given by 2. So it's approximately 3 radians per second. So The frequency is omega by 2 pi, so which is 3 by 2 pi. So frequency in hertz is basically it's about 0.476 hertz. So therefore the ratio of the frequency, so which is omega by omega n, so the ratio R will be 0.476 by 2, which is so zeta is basically given to be 0.15. So now let us write down the equation of motion. So let us for that let us first draw the free body diagram. So the free body diagram for the mass m, it will be like this. So there will be two forces, spring force and damper force. So those two will be acting on the mass. So now how do we write down the uh, spring force? So let us say it is tensile. So we assume that basically x minus y is kind of greater than 0. So the spring force is k into x minus y, and the damper force is given by c, so x dot minus y dot. So how do we get that? It is basically the two ends of the spring and damper are moving at according to the displacements x and y. So this end is moving at x and the other end is moving at y. And similarly for the damper, the the velocity of this point is x dot, whereas the lower point is y dot. So the difference between that basically is the relative velocity and the relative displacement. So that based on that, we can write down the expressions for the spring and damper force. So, so we can write down mx double dot is minus x minus y minus c x dot minus y dot. So alternatively, we can write down m. So we will collect the terms related to the x coordinate on the left hand side and keep the terms related to y on the right hand side. So we can write it as mx double dot plus cx dot plus kx is equal to ky plus cy dot. So which is like a sinusoidally varying force. So this is basically an example of forced vibrations. So to solve for the amplitude of steady state vibrations, we will assume a solution of the form x is equal to some x e to the power j omega t, and y is of the form, let us say y e to the power omega t, and we can substitute this in the differential equation. So then we will find out that so if we take the ratio of x by y and take the modulus of the complex number, we will get the ratio of the amplitudes, which will be k square plus omega square c square upon k minus omega square whole square plus omega square c square. So if we introduce the terms of zeta is c by cc and r is omega by omega n, so this will be transformed into root of 1 plus 2 zeta r whole square upon 1 minus r square the whole square plus 2 zeta r whole square. So we get the ratio of the amplitude of the car with respect to the amplitude of excitations, which is y because of the rho. So we know that y, so we know the amplitude between peaks is 0.2 meter as it was given in the problem. So this 0.2 meter is basically twice the amplitude of excitation. So capital Y is actually 0.1. So we have already calculated the value of R, and we also know the value of zeta, so which is 0.15. So therefore the amplitude x will be 0.1 times square root of 1 plus 2 zeta r square for this expression. So if we substitute the value of zeta, so r we have already found out that it is 0.238 and zeta is 0.15. So if we substitute it in this expression, whole square. And also we need to find out the speed of the uh, most unfavorable speed for the passenger. So that will be when the frequency of excitation matches the natural frequency. So that will be when the frequency of excitation, which is given by pi v by L, or in other words, so if we want to compare the frequency in hertz, so it will be v by L. So that will be equal to 2 hertz. So when v is equal to 70 meters per second. So if you want to convert this into kilometers per hour, so we will multiply 70 into 3.6. So it will be about 252 kilometers per hour. So this is the most unfavorable speed for the car considering the given profile of the road. So which is fairly high. So this was how to solve these kind of problems. So now we can close this session for this week now. So if you have any other questions, we can either take it up in the next session, or if you have any questions for me, you can always post it on the discussions forum for the course. So thank you for joining this session.
Thank you, sir.
Thank you.